All right, so we talked about Newton's first law and his second law in the last videos. And then we're going to finish today with Newton's third law of motion. So before we get too far into it, try this physics warm-up on his laws. So here's the question. It says, describe two different times when the acceleration of your car could be zero. And then what forces are acting on your car in each case, or in each of these cases, when your net acceleration is zero. And then lastly, what is the net force acting on your car in each case? So go ahead, think through those ones and then hit pause to think it through some more, and then hit play when you're ready. All right, so question or part one says describe two different times when the acceleration of your car would be zero. Well, before we get too far, I'm just going to say Newton's second law up here. F net, so that's the overall force acting on your car, is equal to ma. So force is equal to mass times acceleration. So I'm just going to put this here as a reminder, but two times when your acceleration is equal to zero in your car. Well, first you got to think through what is acceleration. And acceleration means your velocity is changing each second. So basically, another way to say this question, or one of your times in your car when your velocity is not changing. Well, probably the most obvious one, when your acceleration is not changing, your acceleration is equal to zero, would just be when you're parked, right? So you're not moving. So if you looked at your speedometer, it's just going to read zero. The second case where your acceleration is equal to zero might be a little trickier, but this would actually be if you're moving but at a constant velocity. So your acceleration would be equal to zero if you're cruising down, say, like Hayes Avenue and going 30 miles per hour and is fixed at 30 miles per hour. Your acceleration would be equal to zero in that case as well. And your acceleration would be also equal to zero if you were not moving. It says, what forces are acting on your car in each case? Well, let's go to the case where you're parked. So in that case, you have your weight force going down, your force of the road pushing up on you, which last time we had a special name for that. That's called your normal force. So if you're parked, your two forces, normal force going up is equal, but an opposite direction compared to your weight, so they cancel. So in that case, your net force would be zero, and your acceleration would then be equal to zero. Now, if you're accelerating, your tires are pushing you forward here. So let's say this is the force of your tires basically pushing you forward going that way. But if your acceleration is equal to zero, but you're cruising down the road, like say at 30 miles per hour, you have your force of your tires pushing you forward. Well, what forces are acting against you? Well, probably the most obvious one is that you have air resistance, right? So since you have air resistance and friction kind of going on there, we'll say force sub R for air resistance or resistance is going against you. And if the force of your tires pushing you forward is equal to the force of resistance going against you, then that means the velocity of your car will be staying constant. That means your net force is also going to be zero. And there's two fancy words for what's happening in this case. We have static equilibrium, which would be the case where your car was completely at rest, versus dynamic equilibrium, which would be the case when your car was moving but at constant velocity. But in each case, acceleration is zero, so net force is zero. All right, hopefully we warmed up your physics muscles, and now we're going to Newton's third law. So Newton's third law, and my guess is you've probably heard this one before. The Newton's third law is written as, for every action or force, there is an equal and opposite reaction or force. And then this is also known as his action-reaction law. So for every action, there's a reaction. So you got action, reaction, and then it says, note, these two forces always act on two different objects. So basically, in order to experience a force, you need at least two objects. So if you've ever stubbed your toe, like maybe you're walking down your hallway and it's dark and you stub your toe and you experience a force on your toe, well, your toe only experienced that force because it encountered a second object. So Newton's third law is basically saying in order to experience a force, you need two objects, and it's an interaction between those two objects. All right, so Newton's third law, just a little practice with this one. It says try to find the reaction force for the following examples. And when you first do these, you might be like, Mr. Laurent, these are ridiculous examples, but it is interesting to think about them, even though they seem kind of simple. So action, Sam punches wall. So Sam got mad. He punched the wall as the action. So Sam's force is being exerted onto the wall. What's the reaction? the wall actually punches Sam back. And you're like, no, that doesn't make sense. The walls don't punch people. But we take it for granted they actually kind of do. Because say as a kid, Sam got mad and he punched the wall and he kind of punched it kind of lightly. If Sam punches the wall lightly, how does the wall punch him back? Well, the wall punches back with equal force but opposite in direction. So if Sam punches the wall punches him back lightly. If Sam were really mad and he punched the wall really, really hard, then the wall punches him back equally as hard. So action, reaction. Here's another one, action. Well, sitting, you push down on the chair. So I'm sitting in my office chair here, and I'm pushing down on my chair. So the question is, what's the reaction? And the reaction, if I'm pushing my chair down because my weight is acting down, then the reaction is the chair pushing me up. And so basically, if this is me, I'm just going to draw myself as a red dot. Looks kind of like a heart there. Let's just make it a dot. There we go. So my weight force goes down. So my force is going down in the chair, but then the chair is pushing me up. And then that's a support force, so we call it our normal force. So the action reaction in this case is the weight is pulling down, and then the normal force is pushing up, and those two forces are balanced. So my net force is 0. And if you ever played a mean trick on somebody, if you pulled somebody's chair out from them, basically you're taking away the normal force, the support force. So what happens is if you were to pull somebody's chair out, when they go to sit down, they won't get that normal force, the support force. So they actually can feel weightless because they don't have the support force to let them feel their own weight. So that's why your stomach kind of drops if you've ever went to sit in a chair but the chair wasn't there. All right, so Newton's third law examples. All right, so we're going to look at actually a really good example of Newton's third law. And so by going through this, I think it'll make a ton of sense. So here's the situation. So car manufacturers will crash test their cars. And then basically once that car is released to the public, then there's other places like the Insurance Institute for Highway Safety, a group called IIHS that will crash the cars as well and give them scores. And they did an example where they took a Ford F-150 and they have crash test dummies inside with all these sensors and probes to measure how much force each crash test dummy takes. But basically they had a Ford F-150 which weighs about 4,400 pounds, 4,400 pounds, and they have a smart car, or a Honda Civic, I think it might be in the video, but basically it's a car that weighs about 2,200 pounds, and they have a head-on collision. And so the question is this: which vehicle experiences the larger force? So they're going to crash them together, and we want to answer the question, which vehicle experiences the larger force? Second question, which vehicle experiences more damage? So basically your choices would be, for each question, would be the F-150, which is the truck on the left side here, or you have the smart car, or you have the same force, or cannot be determined. And then we'll have you pause the video, make your best guess on both questions, and then we'll hit play, and then the video will kind of illustrate the point here. But all right, go ahead, hit pause and think this through. All right, so we're back. Let's take a look at this video. And it says demonstrating differences in compatibility, which this company defines it as, if you ever notice, like a F-150 is very, very large and rides higher than small cars. So they're trying to show not only does a bigger car do more damage, but it does more damage when it rides higher. So we'll take a look here, hit play. There's no sound to this because they've slowed it down. But so it says F-150, if it meets the government requirements for its ride height. So real quick, they're saying compatibility. Notice that this car is riding higher than the Honda Civic. So when these two cars hit at this moment, which one's experiencing the greater force? And if you said they experience the same force, you'd be correct. So since you have two objects here and they're contacting each other, the force has to be the same for both. So take a look at which one undergoes more damage. So there's the after right there. So same force. To me, it looks like quite a bit more damage is on the smaller car, the Honda Civic over here. Let it play out again here. So same force, because Newton's third law, for every action, there's an equal and opposite reaction. So it has to be the same force. But notice the silver car, way more damage. And then now they're saying raised ride height. So if you've ever seen That was a good pause right there, by the way. So this F-150 has been raised up, and I forget, I think it's like 8 inches or 10 inches or something. And they're trying to show why they're trying to put limits on how high you can raise up the vehicle. Because now this vehicle has twice the mass of the silver vehicle, and now it's raised. And now notice it's going to do even more damage. So right there, do you notice the front of this car? This is at 35 miles per hour versus 35 miles per hour. You could picture if they're going like 50 miles per hour, that front of the truck is actually going towards the windshield of the car. So we'll let that play through again. So this would be the raised ride height. And this is a company called the IIHS, the Insurance Institute for Highway Safety. So it's all the car insurance companies kind of got together and made this company trying to figure out which cars are the safest. And you can go to their website, iihs.org, I think it is, and check out your car. And we're going to do that in just a couple of weeks here. Which one experiences a larger force? Which one undergoes more damage? Well, we said the force was the same. Let's go with blue. So the force was the same. So I'm just going to put right here, the force was the same. But we noticed that this car, the smaller car, was way more damaged. And you know from just intuition, or maybe you've been in a car accident before where you were in the smaller vehicle. Why is it the case that the smaller cars are less safe to be in? And to do this, we have to go back to Newton's second law, which says that F equals, see if you remember what Newton's second law is, F equals ma. So if we look for this small car, since it has a small mass, I'm just going to say, okay, Newton's second law for this car is F equals ma. So there's a small m, which means when it gets in an accident, it has a big force. In order to make the equation true, it's going to have a huge acceleration. And now over here for the pickup truck, this pickup truck literally has twice the mass of the smart car. So that means its mass is going to be bigger, which means that its acceleration will be smaller. So if we look here, this big truck has a bigger mass, which means its acceleration is going to be smaller. That means when it gets into an accident, acceleration is your change in velocity. That means this truck isn't going to change velocity very much. Whereas this car, its acceleration is going to be twice the acceleration of the truck. So that's why the safest vehicle you can be in, if you're just looking at size, is always the bigger, heavier car. Because when it gets into an accident with a smaller car, the force will be the same, which means that the smaller car is going to have a bigger acceleration. And being a baseball player back in the day, I remember you'd see it happen where somebody's going to like catch a fly ball, and maybe they're a bigger person and they collide with somebody who's smaller. Well, the smaller person always bounces off the bigger person. And it's not because they experience a bigger force. They experience the same force. It's because the smaller person has a smaller mass, which means their acceleration has to be greater to make Newton's second law true. So this is a really good example of Newton's third law. And a misconception people have is that the force is going to somehow be different, but we know that for every action, there's an equal and opposite reaction. So that's Newton's third law right there. One last example with this. When you push on the ground and walk forward, so you push on the ground, I'm on Earth, picture you're walking outside, your foot pushes on the ground, and the ground pushes you in the foot, right? So this is an example where the force between you and the Earth is actually the force F, and because your mass is small compared to the mass of the Earth, so let's just say this is you over here. This is you walking. And over here, this would be a really extreme example of the Earth. So basically, when you walk on the Earth, it would have an even bigger M, huge M, so really small a. But when you walk on the Earth, you actually experience the same force as the Earth. So you move forward, you accelerate forward, and the Earth actually slightly accelerates backward. But you don't notice that because the mass of the Earth is so much greater than your mass. So yeah, so when you touch the Earth, you actually both experience the same force, different accelerations because you have different masses. All right, so before we go, physics out the door question, Newton's three laws of motion. We've spent a lot of time on Newton's three laws of motion, so by now you should be able to state what each law is, so 1, 2, and 3, and then give an example of each. And then that way, if somebody ever asks you, what's Newton's second law of motion, or if you're ever on a game show like Jeopardy and the whole category is Newton's laws of motion, you should be able to rock that category and win a lot of money. So we'll finish there. Have a wonderful day, and go Physics All-Stars.